problem. So my talk is related to co-design quantum computers. This is a concept that I created in the last probably 10 years of my scientific work, even though it has been mostly used since last year with this coin terminology for the sake of the business development of the company IQM that manufactures quantum computers. So I will be, of course, pedagogic. I've heard that some of you may not be still experts in quantum computers or in quantum physics, so I will just switch from pedagogical comments to more advanced ones, and also the idea is to discuss. So if you have some questions, or you can politely interrupt me at any moment, okay? Fine. So in principle, I have to click on this. My first slide is just provoking you a little bit, and I will be provoking you the whole hour, right? Is concerning quantum physics, and I will try to share with you my opinions, rather strong, on this mysterious field called quantum physics. Typically, we speak about atoms simultaneously being placed into different locations. That is essentially linear superposition of quantum states. Einstein called it spooky action at a distance when we involve entanglement or teleportation, or the quantum parallelism, that is many body systems happening in multiple Hilbert spaces, or the quantum computing as a way of handling quantum information for outperforming classical devices, right? And nowadays, essentially, we are speaking about general quantum technologies. And my final sentence below it is, sorry guys, my opinion, there is no mystery in quantum physics. I work in this like many other people, many years. I don't find, and I don't acknowledge any paradox, any surprising result. It's a fantastic theory, is the most exact modeling of nature we have ever been able to make in history of humankind. And of course, if you have arguments against my statement, we can discuss, but I find it really absurd that we are publishing plenty of wonderful papers that are being verified in the lab, and that we are still claiming that we don't understand. And that's contrary to Feynman's statement. I claim that I understand and we understand pretty well almost everything in quantum physics. And that's why we are making quantum technologies, right? Another perhaps shocking statement for you, or this is my statement of principles in the field, is that I think that fault-tolerant quantum computers are just taking us somewhere in the far future, which is not interesting at all for me. Essentially, I think that none of us will see any useful outcome of fault-tolerant quantum computers. Evidently, I think it is an important research topic, and many talented people are working on that. I don't, right? Essentially, because I want to work for something useful now, and that's going to be my argument in this talk. So I am even tougher in my statement. I think that universal quantum computers or fault-tolerant quantum computers may never be built at the level of scalability that are needed, but I don't think even they will ever be needed because there are many ways of reaching usefulness in quantum computers and quantum technologies, and that fault-tolerant quantum computers are just a wonderful dream, but it is not needed at all. And I will give some arguments to convince you that I think that following these rules or these ideas of co-design quantum computers, we can reach useful, scalable quantum computers in 5-10 years, not more. In this class of co-design quantum computers that I will define in the next slide, we can put coherent quantum annealers, which are being built in some places. I created this concept of digital analog quantum computers. Very recently, digital adiabatic quantum computers, neuromorphic quantum computers, and everything that is the wonderful mixture between brain science, artificial intelligence, and quantum computers, right? So the last sentence of this slide is, do I have futuristic ideas? Absolutely, yes. But I don't work to speak about the future. I work to bring those fantastic ideas to the present and to make useful quantum computers now, right? And as a principle of life, I never work for posterity. Right? I work for useful things now. Every paper, every idea is a reality and a relevant thing that happens in the concepts and in the lab now. And that's more or less my point of view. So here is a pedagogical definition of what I call co-design quantum computers, right? So you see more or less what I mean. Essentially, co-design is not new. The concept is pretty old. It comes from, in fact, you can find even in internet some even centers or institutes in US related to co-design computing in the 50s, 60s, related to IBM, for example, and it is just the design of algorithms, so let's say the software and the hardware hand in hand, such that we optimize the specific application to the possibilities of the hardware. Nowadays, we don't see that much, depending on your field. Many people think that you only have these digital computers, but you can check many companies. I will not advertise any, but you can see many companies trying to develop analog computing, analog quantum computers, and also this way, this merge approach that I call digital analog, right? So that's more or less the idea of the co-design, that we think in the algorithm through the hardware, and we think in the hardware through the application. Then another claim that I do is that we are all speaking about, oh, sad, we cannot make fault-tolerant quantum computers. So let us focus on the NISQ architectures. That's the only possibility, like a loser mentality, right? And in fact, it is true, the NISQ architectures are providing some limitations. For example, nobody is daring to do fault-tolerant quantum computers, because to build a single good logical qubit may take thousands of physical qubits that we don't have. But I claim that with the same technical possibilities that are being used in the NISQ architectures today, we are able to build useful quantum computers. And I also claim that the current digital quantum algorithms, I mean sequences of 1 and 2 qubit gates that are used in the NISQ architectures, are the worst matching to the hardware. And that's what I came up with, these ideas of co-design, right? And one of the examples, just for being pedagogical, because there are many fronts, right, of co-design quantum computers, is this concept that we created some years ago that is called digital analog quantum computing, which is nothing else than the name, right? It is a mixture, an absurd and creative mixture between digital quantum gates with analog quantum steps, let's say, or operations for maximizing the capacities of the software and of the hardware today, right? Which is one of our main goals. I will never walk alone through the quantum winter that has been predicted. You know, some people claim that the quantum winter will take 1 year to 100 years. But I claim that we can be producing useful quantum products since now through many decades, until perhaps one day in the far future we can make the fault-tolerant quantum computers. Right? So this is more or less one slide. Looks like a little old slide, because it is, in fact, right? But I have been adapting it the way I see it. You see there up, the quantum brain. This is my fantasy from the future brought to the present. So I work to combine brain science, AI, and quantum computers, right? In the center is the concept of co-design quantum computers. On the corners is this digital analog quantum computing, digital adiabatic, and below neuromorphic quantum computing, right? I will mostly focus on digital analog, just to exemplify and get you to the topic, right? But that's more or less the way, perhaps, is my brain, my classical brain is kind of displayed in this slide. My co-design strategy from also a business point of view, so that the way we can go in a meaningful manner is that, and that have been overlooked mostly by academia and by companies in software and hardware, is that these co-design quantum computers can go In the central line that you see will be mostly the applications that are crucial for the society, for the tech companies, in fluid dynamics, chemistry, and many others, right? Through the clients, partners, collaborations. But I'm very much interested in the upper branch that you see, that is education. When I mean education, is elementary school education. My experience talking about quantum computing to children from 5 to 10 years old, from 10 to 15, is pretty clear that they are ready to understand and create out of it. And in the lower branch, you see that I put recreation and outreach, because I think that there are ways also of creating interesting, let's say, ludic activities, and also outreach in the sense of, for example, museums, right? And quantum computers in this co-design approach for exhibition and for approaching the community to the quantum computers. As I said, I will be oscillating from pedagogical things to some technical things also, but you can ask anything you want, right? So this is a beautiful set of photographs. The upper one is artistic photography of what we all want to put these classical computers back. I think we will never manage. We will survive with this merge of classical and quantum computers, and below is one of the 9 qubits of Google. This we work in a couple of Nature papers with the friends in Google to produce this wonderful, let's say, fermionic encoding through Jordan-Wigner transformations. Is a Nature paper of 2016. This is, again, some beautiful photographs and artistic designs of different quantum computers, right? And I belong to this group of people that make the difference between supremacy and advantage in quantum computers. So for me, supremacy is when we just outperform classical computers for the sake of anything, right? And advantage, we call it when there is some usefulness. And here, I insist that this concept of usefulness is evidently a human-made. So when we call something useful or useless, there is nothing like a cosmological curse that comes and tells you, oh, this is forbidden or this is allowed. Essentially, it's just a choice of the human beings to call something useful or useless. And I claim that for nature and for the experiments, there should be no difference. If you do the proper encoding of the problem on the software and of the hardware in this co-design spirit, there should be no difference, and the same difficulty should happen for let's say, useful or useless applications. So these are the examples. And I like a lot this slide because this is my influencer activities. It is sad that John Martinez left Google. Many stories and interviews why he did. He invited me to visit his labs after they managed to do this quantum supremacy. I'm very proud because I got some presents, not only a signed copy of the Nature paper of the supremacy, but if you see this cube there, is one of the few devices that the Google team did, not for giving us a present, but for internal use, where you see the 53 qubits inside the 54 qubit chip that produce this with 340 something quantum gates, and you see this like a quantum volume. It's a cool reproduction that is in my office somewhere, I think in Spain, and if it was not brought by the students. And below it is visiting the Chinese institutions, and also IonQ with Chris Monroe, where they are still using my 2-qubit gates for their quantum computers. This slide is a typical European perspective compared to the American one. It's quite similar, but in Europe there is this separation that perhaps is going to be modified soon. Is the pillars of communication, simulation, sensors, and computers. In this moment of the history, it's very hard to separate and differentiate simulators from computers. More if I'm talking you about adiabatic quantum computers, digital analog quantum computers, analog quantum computer simulators. At the end, it could well be that that simulators and computers are more or less moving along the same lines. But that's the way we are seeing in Europe this division also for funding and for research. This is also a minimal provocation for you, right? So Europe sees this sketch of the geopolitical present. The real present is the Parthenon in Athens, where I was there some years ago, massively destroyed. We are struggling to grow up in the scalability and the desired future. The idea of these co-designed quantum computers is that this desired future starts to happen now in the present, and we are not just wishing or willing to to be working for a moment that we will not leave. Right? A little bit technical now, just that you see on the left column, you see this digital analog paradigm combines digital steps. Digital steps in our slang is sequences of 1 and 2 qubit gates or a few qubit gates, while the analog blocks are these massive multi-qubit gates that can happen in two ways, or we are using multi-excitation of the couplings in a chip, or we are also probably using analog quantum elements directly. And this is something that, of course, me being 25 years in the business makes me feel uncomfortable to say very, very trivial statements. But for younger generations, it looks like it is not. Right? The most robust quantum coherent elements, for example, in a superconducting circuit quantum computer, are not even qubits, are cavities, are open transmission lines with capacitors, are continuous or bosonic modes, are nonlinear devices, are Josephson junctions. And we are killing all that possibilities of encoding complexity in the computational sense just to build qubits, where qubits are the most boring, simplest two-level system. And that's why we need so many. We need millions of fault-tolerant quantum computers to be useful. It's just because we are not profiting from the inbuilt complexity of the chips, be trapped ions, be photonics, be circuits, quantum dots, optical lattices. There is a natural quantum complexity inbuilt in the setup, and we have to use it. And that's the idea of this digital analog. This is a slide that I presented also some years ago in my frequent visits to the Google team, just that you see my point concerning this issue. You see these Lego pieces or these blocks, and the provocative question is, can we fly with these building blocks, these square building blocks? And obviously, if you throw them, they will not fly much, right? However, I claim that we are living times where we cannot reduce everything to qubits. And there are times, and there will be probably many, many decades in front, where you want to combine some building blocks that are square, and then sometimes you need an airplane propeller, then you have to use an analog version of a propeller and not reduce the propeller for the airplane just to square blocks, because the things will not fly. I'm not claiming that the beautiful figure of below the slide will fly, but be sure that aerodynamically is better than the upper one. A little technical, digital analog quantum computing. We did this work together with teams in the German Aerospace Center, in Mercedes-Benz, with a group of Frank Wilhelm in Saarbrücken in Germany. And this was a very important statement in a paper of last year, where we are more or less saying, if you want to make the QAOA, that is a well-known optimization algorithm in quantum computers, we just prove analytically and numerically that using the digital analog principles and not fault-tolerant quantum computers, you can go deeper in the quantum algorithms, you can be more efficient, and you can maximize the capacity of the current hardware, even if they are following the NISQ principle. So that's an important paper on how you can use this digital analog. And we were very surprised because independently, last year also, there were two important papers. One of them is published, if I am not wrong, in January last year in Physical Review Letters by the Google team, where they claim that if you use analog 2-qubit gates, and analog 2-qubit gates are just a continuous time or continuous set of gates, you can do better algorithms, or you can go deeper. And then later, I think in August of last year, in a PRX, Physical Review X, of the group of Andreas Wallraff in Zurich, they apply that in this paper, these ideas of the continuous get sets to the QAOA algorithm, and they prove experimentally that if you use digital analog principles, you can do better. My claim is that they are using the same simple square lattice chips, and if you are going to use the hardware of the natural hardware for this kind of algorithm, you will have another level of enhancement. These slides I will just pass fast because these are meant a little bit for experts, but this is one of the pioneering experiments of digital analog quantum simulator or quantum computers that we did with Antonio Mezzacapo, who was my PhD student by some years ago. Now he's a really senior researcher working in IBM in Yorktown Heights for quantum computers. But we propose how to make a digital analog quantum computer or simulator of the quantum Rabi model. And the idea is just to show that if you take this model, that is light matter coupling, that can move from strong coupling to ultra strong coupling to deep strong coupling, and deep strong coupling is very hard to find in nature or probably even absent. And instead of reducing everything to qubits, if you reduce this model, light matter coupling, to qubits, then you need again thousands or millions of qubits to explore the dynamics. And what we did was just to use this digital analog quantum simulator and to play some typical methods of Heisenberg representation, interaction pictures, the game of the signs, composing digital and analog blocks, using Trotter decomposition, all the standard paraphernalia of the quantum computers, as you can see. And then we were able to show, I will not enter into the details because this is quite technical. We were able to show that if you give me in the lab a qubit coupled to a harmonic oscillator in the weak coupling regime, right? And you ask the experimentalist, please increase the coupling to strong coupling and more to ultra strong coupling and more to deep strong coupling. I mean, the experimentalist is going to reply, this is impossible, right? You cannot change the coupling at your will of how light couples to matter. However, we proved in the theoretical proposal that this can be done, and it was done in the lab. And it was a beautiful experiment by Nathan Langford in the group of Leo Di Carlo in TU Delft, where they were able to use, to follow our recipes of composition of the digital analog algorithm. And they were able, these are true data from the experiment, they were able to show that even though the lab had only a two-level artificial atom coupled to a harmonic oscillator in a very fixed regime, we were able to compute or to mimic or to simulate absolutely all coupling regimes possible and impossible in nature. Right? So that was a fantastic result, showing that even going through Trotter decomposition for digital decomposition and digital analog decomposition, and that was the first proof that the digital analog concept is much better. If you do this with digital operations, forget it. Nobody has even tried. It's just impossible. Right? And to finish, to show something, I mentioned also digital adiabatic quantum computer. I will not say much about that, even though we created this already since last year. We are placing very, very key papers, and very soon you will see more where we combine not digital with analog, but digital with adiabatic processes, also for the sake of optimization methods and factorization and many others. And concerning neuromorphic quantum computing that I also mentioned at the beginning, I just wanted to show you a couple of examples. One of them is this paper that was very successful years ago, where we invented from scratch and from pure creativity the concept of quantum artificial life. Probably you know that nature can implement cloning in biological systems, like in RNA or DNA, but there is a well-known no cloning theorem in a Nature paper of last century, at the end of last century, by Wojciech Zurek. It's a paper, I think, of half a page, right? And it is rather simple to prove that it is impossible to clone the quantum information encoded in a qubit because it goes against the linearity and the properties of quantum physics. And then we have to invent something that we call partial quantum cloning, just to allow let's say that the no cloning theorem is not blocking us. And using this partial quantum cloning, we invented, following the Darwinian laws or principles of mutation, of generations, of being born, being dead, social life. And we propose how qubits with phenotype and genotype encoded could self-replicate with partial quantum information. And of course, at the end, after proving that, the key point, to be called it quantum artificial life, we had to prove that the whole package of the multi-qubit system remained coherent, quantum coherent. And we did that in three papers. First, the partial quantum cloning. Second, the proposal of the quantum artificial life, Darwinian concept. And third, we implemented this in an IBM quantum computer. And this is a historic paper for me. I'm very proud of that. And if you ask me what for, it's just because we wanted to do that. We wanted to play the game whether biological behaviors could be encoded in microscopic quantum systems, and the answer was yes. And even now, we continue working on that to explore how this concept of how the quantum information and entanglement propagates through a quantum computer can be used for mitigation of errors, for creating complexity, or for optimization methods, because life somehow contains this capacity inbuilt. So that's something that I wanted to show you, how you can be creative at the artistic level, at the biological level, at the financial level, just by interdisciplinary work between different fields. And the second example on neuromorphic quantum technologies or computers is that probably you know also that the brain kind of work with neurons. I say kind of because it was a long debate at the beginning of the last century where we had to explore whether there were units of information in the brain. And then we proposed the concept of neurons, and it was kind of accepted. The neurons have some models of communication. The famous one, this Hodgkin-Huxley model, with the spikes between them. And given also our interdisciplinary interest in combining brain science, artificial intelligence, and quantum computers with these co-design principles, we decided to go for a quantization of the memristor. Memristor is a unit, is a concept that involves memory, learning process, dissipation, and also the capacity of processing information. As you know, classical memristors are meant to be more efficient in the use of energy, and Hewlett-Packard and IBM since several years are considering even launching some commercial models of classical computers with memristors. And what we did is to quantize it, to explore the possibility. Many people would say, oh, these guys, as usual, whatever you do classically, you just put a quantum in front. Be sure that it is highly non-trivial. I explain you why. I said, memristor is memory-based, has a storage, it has computational power, it has dissipation, it has non-linearity or non-Markovianity, in fact, for having learning capacities, right? So if you go to the fundamentals of quantum physics, you would learn, unfortunately, that the 1 and 2 qubit gates are linear operations, multi-qubit gates are linear operations, that quantum mechanics is a linear theory. So to impose to a quantum system to be non-linear is non-trivial. To impose a quantum system to be non-Markovian, memory-based, is even worse. And to impose to a quantum system to remain quantum while it is also dissipative, that means that it coheres easily because of the interaction with the environment, is even worse. So is it crazy to propose such a thing like a quantum memristor? Okay, we did it. We developed the full theory of the quantum memristors, and we proved that the quantumness is preserved while it is dissipative. We prove of the quantum superposition. We prove, we are trying to check now the entanglement properties. And now we are trying to build this field of neuromorphic quantum computers where the units are not anymore qubits, but are quantum memristors. So we are studying how the quantum memristors compose. What for? First, because we want, right? It is the spirit of the, or because it does not exist. No? That's the essence of arts and engineering, is to create things that do not exist. Then we can explore the usefulness. And one of the most important uses that may have quantum memristors is that given that the unit is already nonlinear, non-Markovian, dissipative, it could be that the composition of quantum memristors may lead to an enhanced quantum computational capacity of these neuromorphic quantum computers, while the boring usual quantum computers are based on qubits and linear gates. And the only way to introduce a nonlinearity in the conventional quantum computers is through measurement in this moment. Huh? So that's the way. I'm always puzzled how people are surprised when you tell them, what are the main applications of quantum computers? All the interesting applications of quantum computers are nonlinear, non-Markovian, learning-based, memory, are dissipative. These are the real uses. And what are the elements and the operations that you do? You do qubits and linear operations, right? And only at the end, through measurement, you recover the nonlinearity. You could say, oh, but that's fine, right? Unfortunately, what is needed is a sequence of unitary operations and measurements, and so let's say a sequence that has only been brought by IBM, for example, very recently, if you check the announcements of the company. It is very tricky, and there are many platforms, trapped ions, for example, which are almost impossible. If you tell to an expert in trapped ions to be able to introduce measurements in the middle of the algorithm, they will start to cry, because it is almost impossible. The lifetime or the time it takes to make the projection of the qubits in trapped ions is sometimes longer than the coherence time of the whole quantum computer. So that's the idea of the quantum memristors, to bring a new toy in this co-design spirit to create quantum complexity for computational means and simulations that can bring the usefulness of the quantum computers now, not to leave them for the future. So yes, this is again to start to finish my quantum brain concept. I repeat myself: brain science inspired, artificial intelligence inspired, quantum computers inspired. All three, for me, are the way to go in this century, at least from a creative point of view. And some of you are young, some not so much. But I invite you to accept the challenges of the century, and to accept this interdisciplinarity. And I also want to provoke you a little more here, and to provoke myself, because even though I had worked in this quantum artificial life, quantum memristors, and neuromorphic quantum stuff for a while, one day I woke up totally confused and surprised when I realized that what I was trying to do was pretty absurd. And I explain you why. The reason is that everything that can be considered as biologically relevant for life at the two levels, at the level of the biological system, let's say DNA and self-replication and creation of life, and also the upper level where this basic life that is already very complex needs higher complexity to create intelligent systems like the brain, is a consequence of complexity, of the presence of billions and billions of particles. So everything that is relevant for life and for intelligence only exists in nature after piling up interactions between very specific systems, matter, and the number of these particles have to be millions and billions and millions of millions and many particles. And what I was trying to do with this neuromorphic quantum stuff was nothing else than taking the behaviors and the properties of these highly complex systems with millions and billions of particles and trying to impose them to the microscopic, extremely simple systems called qubits, right? So when I realized that, fortunately, I realized very late. I realized that some years after we work on quantum artificial lives and quantum memristors and quantum neurons, because perhaps this would have discouraged me at the very beginning. But it was very surprising that the answer is that it is possible. It is possible to take the biological properties and the intelligent properties of matter at the highly complex level and to impose them on the microscopic simplest level of 2, 3, 4 level systems. And this is possible, and that's why we can speak about quantum brain and quantum artificial life and quantum computers. No? So I will end up with this slide. That, as I said, reflect a little bit my nightmares and my happiness every day and night, where I am trying to use these co-design quantum computers to bring the future to the present, to decline speaking about promises and saying, oh, this is just the beginning. I disagree totally with the concept of fault-tolerant quantum computers, where the world record in this moment is between 50 and 100, and we are 6 orders of magnitude behind the necessities for usefulness. So when you are 6 orders of magnitude behind, I think there is a lot of possibilities to do something in between to survive this predicted long quantum winter with some good heating. And this good heating during the quantum winter is called creativity, is called interdisciplinarity. It calls for bold attitudes, business models, design of products, adaptation to the possibilities of the hardware or the software, and not just postponing everything or I will never mention names because that's not the idea, no? But sometimes I hear people talking about fantastic algorithms, and when you ask them, but where they will run, right? Because they have to run in some hardware, right? And they always, the reply is, somebody else is building it, or somebody else will build it in the future. Man, that's not the way it should be, in my opinion, right? So when I propose you a quantum algorithm, I speak about the hardware and I speak about the optimal matching between software and hardware. And that has been true along the history of computing, classical, quantum, and it is my guess that it will be like that forever, right? Forever. That means that the separation of information at the software level and at the hardware level was a pedagogical tool. It is valid, but it is unphysical. And since many years, I cannot think in information without the hardware, and I cannot think in the hardware without the software. It is like extracting the music of a guitar from the chords and the wood and the acoustics. I cannot. I need to associate the scores of the music to the instruments and to the artists. And I think in quantum computers, this is the way to go with this concept of co-design quantum computers. So I stop here, and I would be glad if you criticize me or make some questions or some rebellions against my.
Thank you very much, Professor Solano. With that, if anyone has questions, by all means, feel free to unmute yourself. And I think Kirk here has a comment in the chat here, and he asks if you have any comments or thoughts about co-design involving qubits. So any, I guess, qubits that would have multiple levels versus the sort of 2-level systems that are most common these days.
Yes, that's a very good question. Essentially, qubits have been proposed since years. I mean, in fact, probably 20 years already. You can find papers of qubits, and there are even claims that qubits may be more efficient for processing quantum information and making quantum algorithms. I am not a big fan of qubits from that point of view. So let's say just to replace qubits for qubits is fine. If you find results, enjoy it. My point about qubits and about higher dimensional systems is a little more general, and I will explain you with one example that I hope it is clear to you. Even if you don't know the field, I'm sure you will catch the idea. Right? In quantum field theories, when you have scattering of two fermions, electrons, positrons, you see this is done through the massive exchange of photons in this continuous of photonic fields or bosonic modes, if you want, in particle physics, in quantum field theories. And if you check the proposals for making the quantum computation of this model of scattering, you see that the fault-tolerant quantum computers may need 50 million of qubits or operations or more, right? I mean, in my opinion, this is never going to happen. Never, ever. I cannot imagine. I understand very well the hardware. I'm a theorist, but I understand very well. For me, physics is that, right? And I don't see this coming. In fact, in private, the top experimentalists will agree with me. Right? I will not mention names. And what I mean is that if you go to a superconducting quantum computer and you ask to the people that understand the hardware, which is the most natural and simplest quantum element there, it is called open transmission line. An open transmission line for a theorist is a continuum of bosonic modes. So for me, if I want to mimic the scattering of two fermions through a continuum of bosonic modes and I go to a quantum computer, I will use the continuum of bosonic modes to represent a continuum of bosonic modes. You know, I mean, the density of quantum information there is brutal. If you now reduce, you say, I go to lattice theory and I reduce to qubits or to qubits or to qubits, the number of particles again goes to millions. No? And for me, qubits, cavity modes, and all these are just part of our quantum Lego that we have to accept that we cannot go for a fully universal quantum computer in the next decades. And we should just accept this: qubits, cavity, open transmission lines, vibrational modes, dissipative systems, nonlinear devices as building blocks for our quantum complexity. So my answer to the qubits is more general, of course, but yes, I like the idea. And if my system, for example, spin one systems require 3 levels and qubits, I will use qubits because they are natural. And if you ask the experimentalists, the most unnatural thing in the lab is a qubit. It's very strange. I would challenge you. Can you tell me one system that naturally has only 2 levels? I'm sure you will struggle with that question because all the superconducting qubits, 2-level, all have infinite levels. 2-level atoms have infinite levels. Superconducting qubits have infinite levels. They are all anharmonic quantum systems. So the most natural thing is not to use qubits, it's to use qubits and higher number of dimensions. Okay, how I feel about hybrid quantum classical algorithm? Wonderful. It's not that I feel, Nicole, it's just that there is no way out. The fact that we are classical objects, macroscopic objects, makes that anything that we can extract from quantum physics and quantum computers will be classicalized through measurement, right? So I think in this moment, nobody would doubt that not only the present, the future, and the far future will always be hybrid classical quantum. There is no way out. And in fact, it is the most clever way, because not everything is quantum. If you go, for example, to modeling a microscopic neuron behavior and you find some quantum there, just use a quantum computer for the quantum part of the microscopic biological system. But the classical part, you model it classically. So I am convinced that this is possible. The next question is about the quantum algorithm, quantum hardware, like an annealer. Yes, that's sad. No, again, I will not mention names. I know too much about too many groups and too many companies. But for example, it is sad that some programs in coherent quantum annealer are blocked or are delayed. No? it is because of the desperation to make claims about scalable quantum computers. Everybody wants to compete. Everybody wants the classical platform. Everybody wants the algorithm, the claim. But unfortunately, coherent quantum annealers are very, very strong possibilities to reach usefulness with only 50 to 100 qubits. They are very difficult to build, yes, but even if you build 5 to 10, you are making a strong statement that you are closer to 50 and 200. When you try to make fault-tolerant quantum computers and you have a chip with 100 qubits, you are still 6 orders of magnitude. See, 6 orders of magnitude is a factor of 1 million. It's not 1 million qubits more. It's a factor of 1 million, right? So yes, I am a fan of coherent quantum annealers, even though there are very few in the world. I am sure, and in fact, these adiabatic processes, I am not working directly on coherent quantum annealers, but I am combining the adiabatic aspects of the quantum annealer with digital steps. So I am creating this also branch of digital adiabatic stuff, right? For Clayson, that is from Peru, Arequipa. Oh, that's very good. Arequipa. Arequipa comes from a Quechua word from the Incas, and it means I stay here, because it's a beautiful place. Yeah, you can contact me later. You can ask the email to the organizers, and I can tell you about these engineering simulations. In fact, I have one of my things is that I am a mechanical engineer from education also. So I have the fantasy, for example, to use quantum computers for fluid dynamics, right? My dream is not my dream. I work on that. Navier-Stokes equations in the turbulent regime. So to kill and destroy all the simulators of wind, and to be able to mimic the flow of the water, of the liquids and the fluids and the wind in aerodynamic systems. You can imagine that. And then I ask you the question, how you can solve that? You need nonlinear systems, non-Markovian systems, and so on. What we are using, qubits and linear gates. Man, that's not reasonable, right? What I want to do there, quantum memristors, because quantum memristors provide me from first principles the nonlinearity and the aspects of the fluid dynamics. And that's my suggestion, that we try to explore these merged digital, analog, digital, adiabatic, neuromorphic quantum elements to simulate complexity that involves similar properties. And to Samyak Surti, do you believe then that we are unnecessarily and perhaps stubborn constraining ourselves to a grandfather? Wow, what a question. Cool question. I like it. I like it. Yes. I mean, if you allow me, because we still have a few minutes, this is just, I mean, I always call myself old when I talk to younger people, and I don't mean that I am tired. On the opposite, I feel me younger and creative, and each time I work more, I have more ideas. So I don't mean old like that, right? I mean old in the sense that I have seen too much, 25 years, every day checking all the papers of the whole planet, of the most brilliant minds. And I read history. I like to read the flow of history. And my claim about this is that we just have, we pass from classical computers to quantum computers. And the first thing that comes to our mind is bit. And what we want? A quantum bit. But doesn't mean that that this is the most suitable element. And worse, when you confirm what I said a few minutes before, I was telling you that to get to levels quantum system is very hard. It's very, very hard. You have to, typically, you have some degeneracy, then you have to break the degeneracy, you have to induce an harmonicity, you have to, then, for example, I said, the transmon qubit in superconductors. The third level is there the whole time. The whole work of experimentalists, why the people cry, don't sleep, they make PhD thesis, is how to get rid of the third level of the transmon qubit, because it is in this regime where the third level is close, right? When the quantum coherence is long. And then people are desperate, what I do, how I get rid of the third level. Why you get rid of the third level and you don't use it? For example, if you are working with spin one systems that may require 3 levels, right? That's more or less my philosophy. So to Samyak, I will let you with the following poetical reflection, right? When you think in implementing a model on a quantum computer, right? A model, you mean fluid dynamics, chemistry, financial applications, material design, optimization problems, right? Instead of thinking in mathematics and just in the algorithm, try it and make your effort so that the algorithmization of the problem breathes through the hardware. Respect the hardware. That's my message. That's what is missing, in my opinion, in this one. We are not breathing with our algorithmic ideas through the hardware. And why we have to do that? Because we are not making it for the useful quantum computer now. Right? And the way to make the quantum computer useful now is to accept that our modeling of the algorithm should breathe through the hardware and vice versa. Right? That's the sense of the co-design. Oh, flattering comments. Thanks. I prefer criticism, but thanks for. Nicole, can you repeat that line about breathing through the hardware? Oh, wow. How can I say it in a better way? So let me give you the following picture, right? Picture, it's a picture or a video. You take in your hands the quantum computer of IonQ with trapped ions, of Google and IBM with superconductors, of PsiQuantum with photons. You take it, imagine that you take it in your hands. Even if it needs 20 millikelvin, you keep it, it's in your hands, right? And you're going to behave like creating a wonderful, useful quantum algorithm in this quantum computer. And you're going to do it by blowing through this quantum computer. You see, the wind of your blow is the software, is the information, is the soul of your quantum computer. So better that the blow and the wind flows and breathes through this hardware. And in that way, you get the best. Why you do that? Perhaps because you are passionate by this, you see, it is rhetoric, but it's a poetical figure. But the more pragmatic answer is that we are not making it with usefulness in quantum computers. And the most advanced ideas in the market today, in the academia and in the companies, is to wait until somebody builds 100 million qubits, and we are at 50 since 20 years. So better that you take it poetically and you said, my quantum algorithm have to breathe through the quantum computer hardware. And this is co-design. I design the software, I design the hardware at the same time, and vice versa. So I hope, Nicole, I did it better.
Okay, but realistically, in terms of how to breathe through the hardware, a lot of the platforms don't really offer that much in terms of like giving you information about noise and other things. I know like IBM has the Pulse, but it's only on 1 qubit, and then there is like other platforms. So yeah, which like how do you kind of get around that problem? Do you run like other kind of algorithms to say like
that's a very tough question to answer because you mentioned IBM, right? And I will not mention IBM.
Sorry.
No.
Device manufacturers.
I take your question. It's a valid question, you know. But I will generalize. All providers of access to quantum computers online have a horrible interface that blinds us and makes us believe that quantum algorithms is only a mathematical issue, a computational issue, right? Because the business of the people that are providing access to quantum computers through these platforms is that, right? And given that it is their business, they decide unilaterally what we have access to or not. Is that fair? I don't enter into that question. Is that a business model? I don't enter into that question. I respect it. But given that they are dominant in this moment, most of the younger generations only think in quantum computers through those platforms, through qubits, through 1 and 2 qubit gates. As you said, no pulse gate, no controlling the interaction time, just frozen matrices, unitary matrices. Of course, this is restricting our creativity. What I am telling you is to create the rebellion of the artists in quantum computers. You see, it's more or less like you say, I want to make a painting, and then the people tell you, look, there are only access to 2 colors. Huh? Sorry, you want a circle? No, here only squares. Or you need 1 hour? No, here it's only 1 minute. Man, it's very hard to be creative like that. But don't accept that restriction, you know. And that's why, fortunately, there are many companies, many startups, many initiatives in academia, in North America, in Europe, in Asia. And little by little, we are moving to a more, let's say, democratic and wide possibility of resources. And as I said, if some of you is surprised when I tell you that the most quantum coherent element of a superconducting quantum computer is not a qubit, something is very wrong in your education, right? And we have to correct it. And that's my message. You see, so I am calling for an intellectual rebellion towards the simplistic use of linear gates and 1 and 2 qubit gates and qubits in quantum computers.
I think Marcos has a one last question in chat here of
any thoughts on the application of AI? Yes, very, very good point, right? One of the reasons, for example, why people are trying to build memristor-based classical computers is that also thinking, if you check, you know what are GPUs, you know what NVIDIA or FPGAs are, right? Analog circuits, right? And you know, many important things in AI and machine learning, you have just, the only chance to do it efficiently is using more analog cards. And in quantum computers, it's the same. You know? So I mean, allow me this. I know that some people will be angry. When I was telling you that quantum computers with fault-tolerant concepts needed 100 million qubits, I was very, very polite, right? I was very polite, because if you tell me now big data, AI, machine learning, it could be that the number are billions of qubits. And you know what is worse concerning AI and machine learning and big data? And I also ask, when you talk to an expert in quantum machine learning, people talk about everything except the real problem. What is the problem there? How to load classical data efficiently onto the initialization of quantum computers. Nobody knows how to do that. So if you take me some billions of bits of data coming from internet, you know, people tell you the algorithm of the quantum machine learning, but they should be telling you how to load. And this is an open problem that some of us are working. I'm also working on that. I will not tell you my ideas, but there has to be a more automatic way of loading data. If you don't load data, the algorithm is useless. So let's say the quantum machine learning algorithms are not running on classical computers, are running on quantum computers. How you load the data, and so on and so on. So it's not only an issue of saying, oh, I have my quantum machine learning. I think we are missing the hardware aspects of the quantum computers. And don't be annoyed, right? Because some people say, oh, that's sad because, you know, that's like dirty, right? Oh, I have to think in the noise. I mean, enjoy it. You know? And Nicole was asking me to repeat that about the breathing, you know, but I will tell you another of my mantras and that I said some years ago. I am not ashamed to live the times I live. And the times we live is not of fault-tolerant quantum computers. Right? This beautiful intellectual object does not exist and may never exist. It is the time of creativity, of hardware thinking, of software, of adaptation of hardware and software, of digital and analog, of digital and adiabatic, you know, and that's fantastic. That's fantastic. That's beautiful. You know? And gracias, viva la revolución. You see, I'm not about politics. The revolution of the mind. You know. I don't know you, right? But when I was a child and I wanted to make science, I was very angry when people told me, oh, all these problems are solved. I am happy when there are problems that are not solved, right? So I want to work in fields that are totally complicated and difficult, because there I can make a difference. Right? So if you want that I bring you a quantum computer that works, I mean, you are very lazy, or you are not an artist and you are not a scientist. Scientists, artists want to create things that do not exist. You see? So quantum computing is a fantastic field where we can put all our creativity and where there are plenty of things to do. You see, and some companies may be making you feel uncomfortable, that the only thing to do is just to make 1 and 2 qubit gates in fixed gates that you have online. That's not true. That's the boring side of quantum computers. And I'm very happy, very proud. I don't want to live in the future. I want to live now. The challenges are now, and they are beautiful. Accept it, enjoy it. Thanks to the Miami guys.
Yeah, I was just going to add to that and say, like, definitely even as a club, I think I was literally just talking yesterday to John and to Kirk about how we started with like, oh yeah, like quantum computing, you have the many parallelized states, and you can use the IBM Qiskit device. And now we're like kind of 3 years on, it's like, well, I feel like we should have done more in terms of fundamentals of some of the other things. But the problem that we always had was like the classes that are there for quantum and quantum computing especially are graduate level classes, and we're undergrads. And like if you want to take it, it's like it's basically like a lot of extra effort. So what can we do to kind of like make sure that everyone is learning like some of this stuff earlier on?
Wonderful. That's exactly the question. Huh? The question is now how to solve this, right? And we should go back to our teachers and professors and tell them exactly what I'm telling you, right? Because this is what I tell to my students or to younger people when come and they tell me fault tolerant. Of course, fault tolerant, quantum error correction. Ask the first question. Show me a single logical qubit that is robust enough to scale up to many logical qubits. Inexistent. We are 25 years and nobody has been able to build a single logical qubit that works, right? So please explain me, teach me quantum computing such that I can do something else than that, right? And this goes through learning something of the hardware. And instead of course, you need also, of course, some teachers that really help you to love the stuff, right? I had perhaps this lack. I was educated in the Brazilian school, in the French school, in the German school, where everything that you write as math, you understood like a physical system, right? And I educate my students like that. So it is forbidden to think in, as I said, in the people around me, we have a slang, right? It's Hilbert space physics. This is the worst offense that we can have. If you propose me an idea and I tell you Hilbert space physics, this is an offense. This means that you are thinking in the air about information and where is the hardware, where is the support, no? And that's what we are needing now. And we are needing to go back to our master programs, to undergraduate programs, and to say, guys, we need to understand a little bit how is the hardware of the quantum computer, because we are not even making a single logical qubit. Think it carefully, a single logical qubit. How can you speak about solving cancer problems and designing new drug for medicine or solving if we don't have a single logical qubit? That's the reality of fault tolerance quantum computers. We don't have a single logical qubit. Right? And I'm speaking about research. Imagine that there are companies that are selling stuff when there is not a single logical qubit. That's a little strange to me. See, for making business, you need a product, a quantum product. And this quantum product has to be useful. Right? If you want to make research, you have to make research about a proposal that can be tested in the lab tomorrow or next year. Or it is something that is a conjecture, perhaps in the next 20 years. But you need to know where you are based. And I hardly understand programs of undergrad and master programs in quantum computing that only focus in 1 and 2 qubit gates acting on qubits. I respect it. What can I say? I respect it. I have to be respectful, but I disagree. That's not quantum computing. That's not creating the know-how of the next generations. You will not solve the problem of quantum computer like that. Huh? You will not.
Yeah, that's where I think like we are at a bit of an advantage here at UC Davis, because there's definitely no like quantum computing program like that, and none of the professors are really like honestly very. I think everyone's like pretty skeptical about any of the quantum devices right now, and they have been for a while. and they're working on like color centers and qubits and those kind of systems, and not really even for quantum information, but more for quantum sensing, and then using machine learning or some other classical algorithm to really take into account the quantum sensing. But yeah, I've always felt like like they were a little bit too skeptical, like they're on the other end, like, oh yeah, like this is not something that can happen soon, like this is something that like you should not even focus on computing or whatnot until like you're in your PhD and like you're trying to do that, which I also feel is kind of not the best way of necessarily looking at it as well, right? Like it's kind of the other extreme from what you're talking about as well. It's kind of more in the middle, like take it on, but think about it realistically about how you can kind of use the hardware and whatnot, right?
Yeah, that's right. That's exactly my point, and I perhaps end up with also a challenging question for you, for you all, and it is what I called the cosmological curse. I like it. I like this provocation, right? Because I was very puzzled when Google did claim quantum supremacy with 53 qubits, and then I said, man, we cannot perform quantum classical computers. Perhaps not with 53, but perhaps with 60, but we can. And then my question to myself was, why when I go to a useful algorithm for chemistry, suddenly I need 20 millions, or for a short algorithm or any other? So then I said, is it a cosmological curse against the human being, that when the human being says useful, 20 million qubits, and when the human being says useless, 53 qubits, right? This is a provocation, right? But it's a valid provocation. And for me, I solved that conflict in the following way. I said, no, what is the 53 qubit supremacy? It is qubit sampling, copied from boson sampling, implemented in 1 and 2 qubit gates in the number of 340 on square lattices of qubits where they have 53 qubits active. And that's efficient, and 53 is enough. When you go to say drug design, financial applications, what you should do, you should say, what is the problem? Or option pricing in finance. How I map it in the algorithm, I will not restrict me to 1 and 2 qubit gates and 2 qubits. I will use qubits, harmonic oscillators, I will use analog operations, adiabatic processes, nonlinear devices. I will be compact. And where I go with this algorithm, to a hardware that is not a square lattice of qubits. My hardware will be also a sophisticated geometrical design, topological, with the possibilities of today. And what will happen, that I am sure, and we are working on that, that also for drug design, for financial problems, for material design, you will also check that it is enough 50, 100, 200 qubits or quantum elements. Right? That's my guess, because I don't think that the universe has something against usefulness for human beings. Right? Reflect on that. Why useful things need so much and useless things are enough with 53? There is not, the universe, quantum computers are not selecting difficulty based on what we choose as humans. What is missing is the proper encoding of the problem on software and the proper encoding of software on hardware. That's co-design. And when co-design is properly done, everything that we know now may be useful with 50, 100, 200, 300 qubits, qubits, cavities, or elements. That's my reflection for you.
Awesome. Thank you for going more into depth on that, and thanks for giving such a really good talk. Anyone else have any other last questions for Enrique?
I had just a one sort of remark. So I was looking at some of your older papers here, and I trust you definitely don't seem to be on the optimistic side that eventually we will get to a point where we'll have some form of error control or error correction, or and I think this is from your paper, that quantum control techniques can be used to improve fidelity of gates, but require classical optimization algorithms. So you also feel there's no hope that these optimization algorithms will also be implemented in a quantum computer, or is this sort of a chicken and the egg problem? of which can come
Good
first.
point. Thanks a lot for the question, because now it allows me to balance, right? So I'm not against error correction, or like people call it now more properly, error mitigation, or reducing errors. In fact, we will have to do that always. What I claim is that we have built a universal model of quantum computers based on digital operations with universal codes for error correction that claim that you need between 1,000 to 10,000 physical qubits to encode one logical qubit. And this is not existing now yet, right? And my point is, of course, we need error mitigation, reducing errors, controlling the coherence. We need that. But again, we need, Nicole may be happy if she's still around, right? We need that the control of the errors breathe through the hardware, such that we can say, look, we needed 200 qubits to solve a most important problem in chemistry. Now, because we need to add some error mitigation, we need 300 or 400. But you know, we are passing from 1,000 logical qubits to 10 millions because of the universal theory of error correction. So everything has to be toned down to the possibilities of the hardware. I insist. Think it carefully in the following. This is a provocation again, but it's philosophy if you want, but it is very deep, right? I claim that there is nothing, mathematics, information, nothing exists in terms of computing information, numbers, mathematics, without a physical support, right? I have some mathematician friends that disagree, that they claim that the numbers exist somewhere, not in the matter. But everything that we think has a support, a physical support in the brain. Everything, mathematics, real numbers, complex numbers, wave equations, qubits, everything. And we are playing a game that is very dangerous, claiming that quantum computer can be done in the Hilbert space. And I claim that this may not happen until the next century. So better that we start to associate content of quantum information with the physical support of the hardware, even for error correction. And in that way, if we pass from 200 qubits to 400, it makes sense, but not to millions, because they are not with us now. They are not. Right? And that's it. Right? Otherwise, the quantum winter is waiting for us. Right? Everybody has predicted the quantum winter. Have you heard also that AI is in the third hype wave, right? Third. So we have failed already several times, claiming AI, and we failed, disappear. All the investments done, the companies closing. How many times we are going to resurrect quantum computers like that? And I am trying to work such that we can do meaningful things now. I want to do meaningful things now. I don't know you. You are very young, right? I feel me very bad saying I work, but it will be useful when I will be dead. I don't accept that. I think we can do useful things now with quantum computers. That's my statement. It's almost a life principle. I think it is possible. I'm working on that, and I am proving it. No? And that's my bet. You have to choose yours.
Thank you very much for your answer. I'll see if I don't think if anyone else has any questions. If not, I'll go ahead and stop the recording. And
I'll ask like one last one. Sorry, just because like you brought up the business side of things, and yeah, that's definitely something I was also curious about. So how do you like balance then, like when you say you're trying to pitch a venture capital folk or somebody who is in the investment community like about quantum technologies, do you start with like all the way back, like, yeah, this is why co-design is important and that kind of stuff, or has any of the, in the business work that you've been doing kind of been more like, you know, this is a specific application, and then really just trying to sell on that specific application and hoping that they understand that that specific application is useful?
It is not easy, Samad. But be sure that there are investors that have the capacity to understand, and to, because this requires, as I said, and I am not complaining, because as I said, I have lived long enough to see the flows, or what is called trend, function, hype, you know. And the last decade was the decade of the Hilbert space physics, of the algorithmics, because the qubits improved, some quantum computers appeared, and then suddenly we moved everything to just algorithm applications, exponential gain, blah, 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 right? We did it. In the previous decade, the first decade of the 21st century, was the efforts to try to, or the theory was quantum information that was purely mathematics, and the people in the lab were just struggling, right? In the second decade, the people catch up, and suddenly everybody moved to, algorithms. This third decade of the 21st century, I declare it the decade of the co-design quantum computers. We have to change again our way of thinking, and we have to convince the investors. I'm talking constantly to investors, almost on a daily basis, and be sure that some of them are angry because you are breaking their expectations, but you just tell them the truth. You have to tell them the truth. I always tell them, where is your single logical qubit? Absent. Then what are you talking about? What are you selling? What are you producing? What? Tell me, explain me, right? I sell water, but I don't have water. I sell cars, but I don't have cars. I mean, makes no sense. You have to contrast. But there are a lot of investors nowadays that little by little see the monster coming and start to adapt and to bet for more elaborated programs of quantum computers. And it will happen at all levels, at the academic level, at the master program level, PhDs, at the company, startups, and the technology. It is going to happen unavoidably, and be sure of it. You cannot, let me again, without mentioning any name, any company, anything, you cannot keep offering to your customers useless algorithms year after year. You get my point, right? You cannot tell your customer, look, I made you a quantum algorithm, but I tested with 50 qubits. And then the customer pays $1 million, you deliver. Then 2 years later, the customer comes and says, okay, but it was for petroleum, right? It was for oil, it was for fluid dynamics. What you want another million? What are you going to give me? Another algorithm. Is it useful? No, not yet. How many times you can offer a product, a quantum algorithm that is useless for the customer? How many years, right? And my claim is that this year is the last. So this year starts to change. You have to change the product. You cannot keep offering useless hardware separated from useless algorithm to the customers. You cannot keep them. The product cycle is finished because there is no product. Right? It's very easy, very, very tough to say it, but you have to accept it.
All right, well then this is the year. Everybody get your quantum startup business plan complete. Get funded before the winter comes.
I am working on that, and you will hear from me very soon.
Oh, okay, very interesting. Very cool.
You will hear from me very soon, and from me and from many other people. So yeah, we are trying to create a current and a move toward important investments to accept the challenges, because this third decade of the 21st century, there are people like me that will not accept to go to the quantum winter. We will not go through the quantum winter. We will be here working, producing useful things. And yeah, some people will bet, and I am working on that.
Oh, interesting. It'll be interesting to see, yeah, how that pans out, and definitely wish you all the best with the new venture. And yeah, I think honestly we could probably go on for like another 30 minutes or an hour to talk, ask more questions to you. But thank you so much for spending even this time, traveling virtually to Davis and speaking with us. Definitely hope that one day you can come visit in real life.
Oh, fantastic. I love
systems.
California. I love California. We will do this. Don't worry. Let us be confident that we will all go through this pandemic time, and we will meet, be sure. But anyway, we are in the internet, and we will be working and betting and investing and going also to create our companies to make the difference. We will see us again.
Yes, 100%. Yeah, definitely. Like, yeah, if you guys are all LinkedIn, definitely follow Enrique. and his posts are very interesting as well, and gave me a lot of insight this last year when I was going through the same problem of like trying to figure out this more information about noises and whatnot. And everyone I asked at these companies were like, why would you want to know that? Is that even really that nice? So yeah, I really appreciate it. And yeah, I guess we can stop the recording for now, but thank you so very much for the time and for really giving a very good presentation on